This side now.
Yes, sir. Good evening.
Okay.
Yes, sir. You are live now.
Let them join. Come on.
Three people are already joined. Three people are already joined.
3 people.
Yes, sir.
Okay. So, welcome to another live session of this NPTEL NOC on Introduction to Point-Set-Topology Part 1. As usual, the live sessions are meant for interaction. So, as such, I will be waiting for you to ask your questions or make your comments. Okay, only then I will proceed. Of course, just like last time, I have something on my own also to tell you, but that I will begin according to your questions. looks like you people have some problem with the uploading your questions or some such thing. Okay, maybe we will start a little bit about what I wanted to say. One of the theorems in path connectivity, etc., even for motivating that through the intermediate value theorem, I had this theorem, namely 3.11. Look at this theorem 3.11. It says that X be any path connected space and f from x to r be a continuous function. Given x and y inside x and z between fx and fy. So I am assuming fx is less than fy. Take a point z between them, some real number. Then there exists the w inside x such that fw equal to z. If you had, instead of x path connected here, if you had x to be an interval, then you would have even concluded that this w is between x and y. X less than y to begin with, then x less than w less than y such that fw equal to that. So that was intermediate value theorem in its full form. Now my question is, can you call this as intermediate value property for the space x? The problem is there is no order on x, right? There is no partial order on x. So x less than y, etc. doesn't make sense. X not equal to y makes sense. X less than y or x bigger than y doesn't make sense. So there is no question of adding the extra condition that x less than z less than y here. So this is the best one can say in the generality where x is not an ordered topological space but any path connected space. Right? So this is the best one could do. So now let me come to one of the theorems wherein there is some inexactness has crept in because of this problem. So I will show you that, and I would like to take this opportunity to clarify that point. So this is the problem, this is the theorem. Theorem 3.19. So here I have a subset of R itself. This I denotes a subset of R. It is not an arbitrary topological space which is path connected, just like in the previous theorem, right? So here I am giving you three conditions which are all equivalent, right? What are they? I is an interval, I is just connected, and I is intermediate value property, right? So what we prove here? 1 implies 2, 2 implies 3, and 3 implies 1. Okay, we have proved that, fine. But let us just examine the proof of 2 implies 3. Okay, because I am interested in this IVP right now, intermediate value property. Okay, so I will come to that later on. So 2 implies 3. So what do? I take x and y inside I such that fx is less than fy, and then take a point t between them. T or z doesn't matter. Okay. So now there are some queries. I will come to those queries later. Right now concentrate on this part. Okay. So fx less than t less than fy. So start with this one. The condition 2 says, what 2 says? 2 says that I is connected. From that I want to conclude that it has intermediate value property. So I have to produce a z or w, whatever it is, which is mapped onto t first of all, right? So what I do? I look at the following two subsets, namely minus infinity to t open and t T to infinity open. Okay, so these two are disjoint open subsets restricted to I. Okay, and look at the intersections here. Look at the two intersections. That will be a partition, that will be a separation for I. All elements of I are contained inside minus infinity to plus infinity. But if T is not there, then I can take minus infinity to T and T to infinity, avoid T, avoid this point T. So the entire thing is connected. Therefore, this will be a contradiction to the hypothesis that I is connected. There is a separation here, right? So the first part here is contain A, this part can B, and A has X and B has Y, because X is less than T and Y is bigger than T. So they are non-empty also, right? So this is a contradiction to what? To the hypothesis that this T is not in I. Okay, so this is an interval. So the contradiction means what? Every point between these X and Y are in the interval. Right? So this should be the proof of, this should have been the proof of that it is actually a intermediate value property also. But what we have proved here, intermediate value property, we have just proved that if you just use connectivity, then it only says that this T is in the f of I, or arbitrary function f. Okay, look at this proof. It only says that the point T is in the image of Fi. Okay, so that is not actually the intermediate value property. Okay, so in the proof presented here, this was not completely proved that it has the intermediate value property as we understand in the analysis. Okay, so this can be modified by putting this extra thing which I have not put during the course. So I have put it and added. So what I do, I actually prove 1 implies 2 and 2 implies 1 directly. Then I can, instead of proving 2 implies 3, I can actually prove 1 implies 3 very easily and 3 implies 1, and that will complete the proof. Okay, so this is one way of taking care of the gap here in the proof. All right, there is another way of doing this one, namely introduce another concept here. This is what I will explain now. So this again I have done later on. Going back to our starting theorem, the path connected space having property something like intermediate value property, which was not exactly intermediate value property because the space doesn't have any order, right? So such things we would like to take care as weak intermediate value property, some name. Okay, so it is not fully intermediate value property but weak intermediate value property. What is it? If for every continuous function f from x to r and x1 and x2 given inside x, fx1 less than fx2, t is between fx1 and fx2, for all such t there exists a z belonging to x such that f z equal to t. So z itself cannot be compared with x1 or x2 because there is no order. So such things we can call it as weak intermediate value property. Now instead of this theorem we have a stronger theorem here. So this theorem 1, 2, 3, where is this? This was theorem 1, 2, 3. We actually have a stronger theorem here. No extra efforts are needed. Okay, just you have to understand what is going on, that's all. So this is the stronger theorem here. Namely, take I to be any interval inside R, R to be any subset inside R, then these four things are equivalent. What are they? I is an interval, I is connected, I has intermediate value property, I as just weak intermediate value property. Okay, even this is equivalent to having the strong usual intermediate value property. So this is what now whatever discussion I have done. So these four things are equivalent. Indeed, the theorem that I have stated and proved, previous theorem here, amounts to proving that 1, 2 and 4 are equivalent. The 4 is a weaker condition as such, but for subsets of R, the same thing as intermediate value property. Okay, so I repeat, what I need to prove is only a part of this one, namely, whatever you have proved in 3.19 amounts to precisely proving 1, 2 and 4 are equivalent. The 3 implies 4 is obvious because 3 is stronger than 4. So what we need to establish is 4 implies 3 or 4 implies any one of them. So we have already proved that 4 implies 1, 2, not 3. 1 and 2 we have proved, right? 4 implies 1 we have proved. So if you have proved 1 implies 3, then you are wrong. Right? So 1 implies 3 was not exactly proved. 1 implies 4 was proved, but in the name of 3 in the word theorem. So you have to do 1 implies 3 only. Okay, for this, all that you have to do is start with any function, f from I to r, x less than y inside r, fx less than t less than fy. You have to produce a t between x and y, right? So all that you have to do is restrict this function f to only the interval xy. Okay. So one is that the first condition is that I is an interval, right? So if x and y are given and x less than y, the entire interval xy is contained inside I. That is the meaning of interval. Now function f can be restricted to x comma y. Okay, so that is also an interval. Now you apply the weak condition, there will be some z such that f of z equal to t. So where is the z? It is in xy. But now look at this point z, it is in xy and f of x less than t less than y. So fz is t. So it is not equal to neither fx nor fy. So z cannot be equal to x or y. Therefore z is precisely inside xy. Okay, so that completes the proof. So again here a typo, z is in xy here. So this is what I wanted to tell you on my own. Now I can answer your some queries and something more, whatever discussion we had last time. So that can also be taken. There was some person called SG. Who was that? Saurav Ghosh? Okay, let us look at what is this Dhansekar wants to say. X is an uncountable set equipped with the discrete topology. Then X is second countable but not first countable. It is not even second countable. There is an example of that. Don't you see that? In a second countable space, every subspace is second countable. So if it's a discrete space, it cannot have a discrete space which is uncountable, because then singleton points, uncountably many of them, they are open. You cannot have them covered by a countable set. Over. Okay. So that was an example of whenever you have a discrete uncountable set, such a thing cannot be second countable. Okay, so that question is taken care easily. And the discrete spaces are automatically first countable because the only singleton A singleton A for each A inside the discrete space. That will be a local base. So you have not only a countable base, you have actually a finite base there, right? Local base is possible there. That's okay. Yeah, Saurav Ghosh has answered it correctly. All right. Is this Saurav Ghosh the one who asked some question last time? For which I had given some hints but not the full answer. This cannot be true. Such mistakes cannot have occurred. We will check whether there is such a mistake, there is such a error in assignment 9. I can't go on your assertion. Okay, right now you understand that this is wrong. A second countable space cannot have an uncountable discrete subspace. If you have asked some questions in the forum which are not yet answered, you can repeat them. I will answer them right now. I still think that you are not reading it correctly. Maybe you can read it again. I will check it on my own and tell you, and it will be taken care of. Last time, one of you, SG, I don't know who the full form of him, whatever, he asked some question about a compact subspace being dense in a non-compact subspace. I told him that this must be easy to give and so on. I gave him some hint also. But where is he? Does he want a proper answer? Has he found an answer? Look, just you to ask question, that's not the end of it. You have to learn it correctly. No. So I have told you that is precisely why I have arranged one more session here. Precisely because you wanted more sessions. So what is the answer? N union infinity. Looks like you have got it correctly, but just N union infinity is a set. What is the topology? The singleton infinity becomes dense and compact. How? That's also correct. And what is the full topology? That's what you have to tell. Without that, finally N union infinity should be non-compact. Singleton infinity is compact. Singleton sets are always compact. So you have to make it dense in the whole space. So how you do that? What is the topology? You have to still say. So U union infinity, U subset, union empty set. Yeah, so this is correct. What is doing? Take any subset of N, any subset, empty set, leave it like that. If it's non-empty set, okay, non-empty set you take, you add infinity inside that, U union infinity. Okay, so declare them as open sets, all of them. Okay, so U union infinity, and of course empty set has to be there as a set. So that is a topology. That's what you have to verify. And then what you have? Infinity, singleton infinity is in every non-empty open set. Therefore, it is dense. Okay, dense means what? It should intersect. A subset is dense if it intersects every non-empty open set. So here, every non-empty open set looks like something union singleton infinity. So that singleton infinity is there in all of them. Okay, this space is non-Hausdorff, obviously, but it is not even a T1 space, right? Can you see that? because singleton infinity is not a closed set. In a T1 space, Frechet space, every point must be closed. So non-Hausdorff is easy. Okay. Now I am telling you that it is not even a T1 space. Can you see that? Why? Because infinity is not a closed set. Just now we said infinity is dense inside the whole space. So it could have been Harshit Singh has his problems, but I am not the forum for addressing such questions. Sorry. Okay. So, let us come to this example. This example is not even a T1 space. Saurav Ghosh, I asked, can you get an example? Other things are fine, but can you make an example in which it is T1 also? It must be T1, but it cannot be T2, that we know. Okay, your example cannot be T2. Can you make another example? This example will not do because singleton infinity is not closed. Okay, another example in which the space is T1, non-compact, but it has a subspace which is compact and dense. Okay, can you do that? Harshit, this kind of problems have to be addressed by somebody else. I am not involved in gate EEC maths and so on. And this is not meant for, preparing you for gate exams and so on. Non-Hausdorff T1 is fine. But what is a compact subset which is dense? Zero one with usual topology is compact, not with co-countable topology. You have taken co-countable topology, no? Yeah, that's a good observation, right? So if you throw away a countable set is open is what he wants to say. Okay, if you throw away all the Q, you throw away all the Q, complement is open, Q is countable, no? If you throw away all the Q, is complement open? The complement of the rationals, its co-countable topology, is an open set. Is it open in the usual topology? See, not all countable sets are closed in the usual topology. So, it is coarser is not correct. You tried, it's a good try, but it's not correct. So you haven't understood my point. Each set of rationals, is it closed in the co-countable topology? Is it closed in the usual topology? Therefore, what is the conclusion? Co-countable topology is not coarser than the usual topology. They are not comparable. Right? So your argument is wrong. You have tried nicely, but yeah, so sometimes things don't work. So here I will give you an example. See how to understand what's going on. Your own example, you took infinity, okay? Infinity being singleton, it's compact. Infinity singleton point is compact. So what you do, you put it in every open set. So it became dense, right? So all that you have to do is, you should not work with a single point, because then it's not going to be closed. You should not work even with a finite set, because in a T1 space, finite set will be closed. So you have to do it, one single infinity won't do, you have to do it with an infinite set. There is the only chance that infinite set in a T1 space need not be closed. Okay? So same construction that you have done, you should do not with one single point, but an infinite set. So n itself is infinite, you have to add another infinite set. You understand? So maybe I will leave it to you here to modify your earlier construction. Okay? Now you have to make a topology wherein an infinite set is compact and dense also. In fact, we can make it open also. The singleton infinity was open in the whole space. Okay? So try that. Try that. Maybe if you get an answer, you can, I have told you, you can communicate with me with Gmail, which you have done. Okay, you have my email address. You could have done that one. All right. There's still 15 minutes more. If you have more questions, come up. You know, density, normal density, etc. is a very fragile properties. I don't have a ready-made answer to your question. But the point is, they are not pure topological properties, first of all. They are embedded properties. Something is open somewhere does not mean that the same homeomorphic copy is open somewhere else. Something is closed doesn't mean that the same set will be closed somewhere else. Right? Similarly, under continuous image, it's even more difficult. Okay, so my guess is that this should be easily answered in the negative. Can you do that now? There are many methods of constructing continuous functions. What is one of the construct continuous functions? Taking quotient spaces. Right? Is, is, is this a valid example? A function from 0 1 to 0 1, okay, the Cantor function is not defined on the subsets, on the space 0 1. Okay, the Cantor function, see, f of z 0 1, it does make sense. It is not a function on the points of 0 1. See, it is function on intervals, set of intervals inside, or take an interval, the Cantor function assigns two disjoint intervals. It is not taking a point and assigning another point. So you have to understand this Cantor function. The Cantor function is defined not on points of R. It is defined on subsets of R. What are they? Intervals. Take an interval, okay, delete the one third, middle one third, you get two disjoint intervals. So that is the Cantor function. If you repeat it and take the limit, you will call it as Cantor function. The Cantor set is assigned. So there is no question of f being continuous and so on. So you have put a topology on the set of intervals of R. If you have put a topology there, then you can talk about whether this is continuous and so on. But that is not the point at all. Okay? So you are here, you are totally off the line, off the mark. Now you are asking a valid question. Does there exist a continuous function 0, 1 to 0, 1 which maps Cantor set to 0, 1? So you can make this makes sense, but this is obviously wrong. Obviously wrong because what? The Cantor set is what? Totally disconnected. It is disconnected, right? How can you map it to the whole of 0, 1? Because 0, 1 is connected. The image is connected, right? So what kind of map you have is the question, right? So, okay, sorry. Continuous function 0, 1 to 0, 1 which maps Cantor set to 0, 1 is what you want, right? So your question makes sense, but answer is not that easy, right? So your question makes sense here. The Cantor function, you have a problem. You haven't understood what is the meaning of Cantor function, I think. You have to go back and read it correctly. Cantor function is not defined on points of 0, 1. It is not a function from 0, 1 to 0, 1, I told you. It takes an interval and produces two disjoint intervals and repeat it. The two disjoint intervals become four disjoint intervals in a systematic way. Right? So, it's a function on intervals of R. But your question, this does there exist a continuous function? Forget about 0, 1. Cantor set on to 0, 1. Cantor set is defined in a particular way. That is a topological space. It's a subspace of 0, 1. Okay? So you want it to be such that you have a surjective function to the entire interval 0, 1. Once you have that, you can use T-extension theorem, but which you have not done yet, of course. Then you can extend it to 0, 1 to 0, 1. Okay. So maps Cantor set to 0, 1, that's important. So just think of a function from Cantor set itself to 0, 1, which is surjective. So that is your question. So that one has to think about it. But the way you have talked about Cantor function, okay, Cantor function is something else. It is defined for on all set of all intervals, closed intervals in in R. So good trial. You know, first of all, when you express things in ternary expansion, okay, so you have to, for example, how you write the number 1 by 3 in the ternary expansion, you have to write it as, you know, you can't, you have to take it as iterated infinitely many times. Okay, so once you have understood that, okay, base 3, that is ternary expansion, so all the ones replace every digit strictly after the first one by 0. Okay, so problem comes when you want to say that why this is continuous. Okay, so you have to prove that it is continuous. So if you replace all the zeros, all the ones by 0, so you will have only 0, 2, 0, 2 except the first one. Doesn't matter. Okay, why the first one should not be replaced? It's also a question. Okay. So you see, you meant this whatever function you have defined just now as a Cantor function. Okay. But what I had was I had announced some Cantors in the construction of Cantor set. I have put some Cantor function there. So that was different, right? So you are talking about something else here. Okay. So work out. The question is continuity. Okay. Any more questions? If there are no more questions, now time is up. We can stop here. I want to make this announcement again, which you might have seen already, that next Wednesday there will be another session. For that session, of course, you are welcome to ask your own doubts, but I will have some other thing in mind. Namely, I am going to make a game out of this session. So what you have to do is you have to be prepared with a number of small, not very small, A4 size paper. You take them and make strips of paper. Okay, like if you have A4 size paper is not there. So So it doesn't matter. So if you have paper like this, make strips like that. Okay, 10, 15 strips like this. Make strips like this and have some staples ready with you, okay, before attending the session. So we will make some game of cutting papers and making some topological models and so on. All right? So thank you. So we can now close this. Yeah.